Excuse me, sir.
Yeah, hi.
Hi, sir. Sir, ISI Delhi website is not working since morning. So can you send the latest updated notes on email?
Okay, okay. Uh, you are not able to access my web page or the EPU web page.
Now it is working. Earlier the website was not working.
Okay. But anyway, I will send you the slides also.
Okay, sir. Thank you.
Okay, so let's get started. Maybe others will join. Um today we're going to talk about optimal auction design. So this is optimal single object auction design, and obviously I'm going to tell you what does optimality mean, what is the context, and so on. But it is in the single object auction model, and we have already laid the foundation for it. So I have given you all the tools that we need from last few lectures. So we'll just use that and think about this. Okay, so this is based on this paper by Roger Myerson in Mathematics of Operations Research in 1981. I should also say that Myerson was awarded the 2007 Nobel Prize, primarily based on this particular work. Okay. Okay. So, what is optimal auction design? So, the model is the following: a seller is selling a single object. For the lecture today, let's assume that the seller has no value for the object. So she is primarily interested in getting rid of the object and getting some revenue out of it. Okay. So later, towards the end of the lecture, tell you how it extends if the seller has some reservation cost for the object also. Okay, but for now, let's assume that that's zero. Okay, so the question in the paper is what mechanism maximizes the expected revenue of the seller? And we know because it's of the revelation principle that we can put the same question as what direct mechanism maximizes the expected revenue of the seller. Okay, and the constraints on mechanisms would be incentive compatibility and individual rationality. And Myerson uses Bayesian incentive compatibility and interim individual rationality. So it's a pure optimization problem. You can think of this maximization of expected revenue as some kind of an objective function, and the two constraints are two sets of constraints are basically the Bayesian incentive compatibility constraints and the interim individual rationality constraint. Okay, so before we dive into the problem, let's first pause for a moment and think how we will solve it if there is just one agent. Okay, so it might seem that maybe the one agent problem is too trivial, but I'm just going to give you a two-slide sketch of how the one agent problem can be solved. And basically, um, even there are a lot of non-trivial steps that needs to be filled in. Okay, yeah. So there's a seller and there's just one buyer, and the question is what is the revenue maximizing mechanism for the seller. Okay, so the buyer's value is distributed between 0 and b with some prior capital G, which has a density small g, let's say. And let's for the moment assume that we will only use deterministic mechanism. Okay. So if you're going to use deterministic mechanism, we know that incentive compatibility means that such a mechanism must use a cutoff allocation. Okay. Note that for one agent, Bayesian incentive compatibility and DSIC is the same, right? Because there is just one agent. So both BIC and DSIC is the same concept. Okay, so both of them would imply that the allocation rule is non-decreasing, and if it is deterministic, then it has to be a cutoff rule. Okay, so the seller has this. If the seller imposes IC constraints, essentially for a deterministic mechanism, all he can do is announce a cutoff, and above the cutoff, he will award the object to all the types, and below the cutoff, he will not award the object. Right. So if the buyer comes and reports a type which is below this cutoff, he won't give the object to the buyer, and above the cutoff, he will allocate this object. Okay, and of course, we know that IR means that P0 has to be less than equal to 0. But because we are maximizing revenue, you can basically see that P0 has to be equal to 0. Why? If P0 is less than 0, then essentially the seller is going to lose revenue. Okay. So revenue maximization and IR would mean that P0 is equal to 0. But then this deterministic mechanism is basically what is a posted price mechanism, because we know that whenever P0 is equal to 0, and it's a deterministic cutoff allocation rule, a DSIC mechanism is if you win, you pay the cutoff. If you lose, you pay 0. We know that from our last lecture, right? So essentially, this cutoff point is the price, the posted price. Basically, if the buyer announces, if the buyer has a type above the posted price, he gets the object. If he has a type below the posted price, he does not get the object. So this is what is called the posted price mechanism. What is the expected revenue from a posted price mechanism with price P? Let's say, suppose this cutoff point is P, then basically only types larger than P win, and the probability of that event is 1 minus GP. And whenever they win, they pay P. So the expected revenue is P times 1 minus GP. Okay. So the choice is about choosing this cutoff point P, right? So this posted price P. So to maximize expected revenue, the seller must maximize this particular expression. Okay, so maximize over all possible cutoff points where P is greater than equal to 0 and P times 1 minus GP. Okay. So this is a standard optimization problem, and one can solve this. Uh, So important point to note here is that revenue maximization by seller is ex ante and not ex post. So this is not a, this is not a maximization where I'm trying to maximize the revenue of the seller after every type is realized. That's just not a well defined problem in the first place, right? So I mean, it's not clear that we can find a mechanism which will maximize revenue at every possible type, right? So that's not possible. What we are doing here is, before the seller enters inside the mechanism, okay, he's choosing between all mechanisms, and he's trying to see which one will maximize its ex ante expected revenue. Okay, so this exercise is a completely ex ante exercise of the seller, and hence we see that it is it will involve wastefulness, because generally this P will be strictly greater than 0. So that means that for some types, the seller would not sell the object, even though the buyer may be willing to pay a lower price. It will not do so, and it will just not sell the object to such types. Okay. So it is wasteful. So mechanism does not sell the object at some types. Okay. So this is an important point, because you might think that how is it that the seller is maximizing revenue by not selling the object at certain types? Well, if you think about it, if the seller were to sell at every possible time, right, then the only choice of a posted price is P equal to 0. If he sets P equal to 0, that's the only way it can sell to every possible time, right? Because he has to set the posted price before agents report their type. So it can't be that once people report their types, it announces another price and so on and so forth. So there is commitment now. So the seller commits to a posted price, and when the buyer announces its type, he has to sell the object at that price. And so it's possible. The only way sale at every possible type is feasible is if the posted price is equal to 0. But that mechanism earns an expected revenue of 0. Okay, so you can clearly do better by pushing this price further, but you should not push it all the way to, let's say, the upper limit of this interval, which is B. In that case, you will never sell the object. So the trade-off is basically, selling at a very low price and not selling at all. And so the optimal price, posted price, will be somewhere in the middle. Okay, depending on how this objective function is.
So the
Okay.
implicit assumption is buyer think that there is 100% commitment from the seller.
Yes. So the whole model assumes commitment. Otherwise, this revelation principle will not work. So we often see, in let's say government, right? So government sets a reserve price, and if the sale doesn't happen, then next year the object is resold at a new price, right? So these kind of things are outside this model, because that induces a very complicated game, because then agents today will have to anticipate what the future uh, posted price would be if the sale does not happen today, and so the equilibrium of the game itself will change in that case.
Okay, sir.
Okay, any questions? I think it's important to appreciate the one agent optimization before we go further. Of course, what?
So,
Yeah, go ahead.
so you said that the optimal price will be somewhere in between two prices.
Between the upper and the lower interval, it can't be at the extremes of the interval. That's all I'm saying.
So how do we get that interval? I mean, I don't get it. How that interval will be calculated?
No, that interval is given. So I'm just saying that look at the type space. It's a closed interval 0b. All I'm
Hmm.
saying is that the price can't be 0 or price can't be b.
Okay, okay.
Okay, because if we set it equal to 0, then all the types will buy, but that
Yeah.
generates a revenue of 0.
One term will be zero.
The expected revenue will be 0.
Okay.
Okay, because I'm always getting a revenue of 0. uh,
Yes, sir.
but if we set the price too high, let's say at B, then no buyer will buy it. So all I'm saying is it has to be in the interior of that interval.
Okay, sir.
Okay.
Will this hold for multiple agents also?
Yes, it will hold for multiple agents also. Yeah. I mean, we'll get to the model, multiple agent model. In the multiple agent model, the type spaces of the agents may be different also, but in general, the principle is the price should not be too high or should not be too low. If it's too low, then the revenue will be too less. And if the price is too high, uh, then basically the revenue will again be low because very few types will buy. So in the multiple agent model, it's not even clear that it will be a posted price mechanism. It might be a more complicated mechanism. Okay. Uh,
Okay.
so what? So what I have not discussed in detail here, I kind of hand waved at it, is that I restricted attention to only deterministic mechanisms. So the question is, does randomization improve expected revenue? Can I do better by basically, allocating with, only with certain probability to certain types? So instead of announcing a price and allocating everyone above that type with probability 1, can I have a more, non-deterministic but monotone mechanism? Okay. It's not clear, and you'll see from the results today that randomization does not help. So randomization is not required for maximizing expected revenue. Okay, so and of course everything I have said so far is for one agent. How does this extend to more than one agent? Because remember, with more than one agent, even the deterministic mechanism, the cutoff points may depend on the types of the other agents. So it's not a clear posted price mechanism also. So how do we extend that to more than one agent? Okay. So that's what we are going to do now. So we are going to look at an n agent problem. So each agent has a type space, which is this interval 0 bi for agent I. And these BIs can be different. So potentially we are allowing these agents to be heterogeneous in the sense that some bidders might have very high value for the object. Some bidders might be, might have low value for the object and so on. Okay. And we also allow that the priors or the probability distribution using which agents are drawing from these types space is also different across agents. So capital GI and small GI are basically the CDF and density of agent I. And we are going to use this notation. Essentially, we are going to assume that, agents are drawing their types independently. So basically, the probability with which T minus I happens is just the product of GJ TJs. Okay. So it's independence. If you want to ask some questions, please ask through audio, because sometimes I don't see the chats. Okay, so just use the audio to ask questions. Okay, so two things are going to be important, just like in the Bayesian incentive compatibility case. We know that we only need to worry about interim allocation probabilities and interim payments. So we know what these terms are. So given a mechanism F and P, the interim allocation probability of agent I with type TI is the expected probability with which she will win the object if she reports type TI and others report T minus I, where others are reporting truthfully. Okay. So assuming that others are reporting truthfully, then this is the probability with which she will get the object, and this is the probability T minus I is realized. So this is the interim allocation probability. Similarly, this is the expected payment of agent I with type TI. And we know that Bayesian incentive compatibility requires that an agent with type TI does not manipulate and report type SI. So we have seen this in the last class. And interim individual rationality means that the interim payoff or the interim utility of every agent and every type is greater than equal to 0. So Ti alpha I Ti minus pi I Ti is greater than equal to 0 for every I and every Ti. So these are the two constraints on the mechanisms. So we are going to require that every mechanism FP is Bayesian incentive compatible and interim individually rational. And basically, you can ask that why BIC, why not DSIC, why interim individual rationality but not exposed IR? Well, we want, at the outset, we want to have a very large class of mechanisms. So hence the constraints have to be weak enough to cover all interesting mechanisms. For instance, we want to cover first price auctions. So hence, basically, we don't want to impose DSIC because that rules out first price auctions. So, and importantly, we want to allow for randomization. Okay, so ex ante, we don't want to rule out randomization. Okay, so we don't want to rule out randomization, and our constraints are weak enough to cover BIC and ex post IR. Okay, so give me 2 minutes, I'll be back. Just think about this, and if you have any questions, just think about it. I'll be back in 2 minutes. Yeah. Any questions?
No, sir.
Okay, good. So, so three things. First, IR constraints are weak, IC constraints are weak, and it allows for randomization. Of course, if you have some other solution concepts, you can impose them as constraints also. But at this point, we are just studying some standard incentive and participation constraints. Okay, so it will be useful to write down the expression of expected revenue of a given mechanism FP. Okay, so so this is what the mechanism designer, the seller here in this case, would be computing before committing to a mechanism FP. Right. So when she's thinking about the mechanism FP, she's thinking that if she implements this mechanism, which is, let's say, Bayesian incentive compatible and individually rational, then basically the expected revenue that she will get from this is this. What is this? Well, at type profile T, agent I pays PIT, and this is the total payment that she receives from all the agents at this type profile. This is the probability with which this type profile is realized. And so this gives you the expected revenue from this mechanism.
So GIT is different across agents, so shouldn't it be GIT, summation over PIT?
Yeah, so when I write GT, it means the product of GITs, right? So that's why I have put a bracket here. And this integral is over the entire type profile. So essentially what I am writing here is I am compressing this notation in some sense. This is actually n integrals, okay? And this is like product of G1, T1, G2, T2 till Gn, Tn.
Okay, sir.
Okay.
Sir, why are we only considering independent priors?
Right. So if you remember in the last class also, the tools that we have developed in the last class only works for independent priors. If we have correlated priors, we will cover that also. This toolkit, this Meyerson's framework will not work. This kind of methodology will not work. But I'll tell you in 2 lectures, basically, if you have correlated priors, how you can do revenue maximization.
Okay.
Okay, so right now it's only with independent priors. Okay, so again, what I'm doing here is in the second step of this, I'm again using independence. So what is happening is, I have kind of disentangled the t minus I integral. I've taken the summation outside and basically first integrated t minus I and then integrate over ti. Okay. So if you do that, this the t minus I integral is just pi I ti, because this is exactly my interim, interim payment, right? So interim payment is my expected payment if I has type ti. That's exactly the term. Okay, and so you get this alternate expression, which is kind of intuitive. So either you integrate over the payments collected at every type profile, or you integrate for every agent I his expected payment at every type. Okay, so it should be the same, and that's what this is showing.
Shouldn't it be GITI?
Oh yeah, this should be GITI. Thanks. Here also GITI. Correct. Okay, so there's a typo here. It should be small GITI. Okay, so so this expression is easier to handle. I mean, we'll use this expression instead of this, but basic idea is the same. So what is an optimal mechanism? A mechanism is optimal if it is a solution to the following optimization program. Basically, I'm maximizing the expected revenue across all mechanisms which are Bayesian incentive compatible and interim individually rational. Okay, where expected revenue is this particular expression. We have already computed this. Again, this should be small GITI. Okay. Sorry for this type. Okay, so we computed the expected revenue here. So this should be just to maximize this expression subject to BIC and IIM constraint. Okay. So what we are going to do now is to use what we have learned in the last class. Okay, let me, so there's a request to turn off my video. Let me do that. Okay, so suppose FP, we know that from our last class, last lecture, that if FP is a mechanism which, and the priors are independent, then the following two are equivalent. FP is BIC and IIR, and F is non-decreasing in expectation. So the alpha I is non-decreasing, and for every I and every TI, pi I TI is determined by this formula, and pi I 0 is less than equal to 0. And so the second one is basically the IIR constraint, and this is the revenue equivalence formula. This, along with non-decreasing in expectation, is necessary and sufficient for FP to be BIC and IIR. So instead of imposing FP is BIC and IIR, we can just replace it by F is non-decreasing in expectation, and this inequality and equation holds. Okay, so what I'm going to do is basically use this result to show you how we can simplify the objective function. Okay, so remember the objective function has a pi I ti term, and we know that pi I ti is equal to this for any BIC and IIR mechanism. So we can always substitute and replace it. Okay, so what I'm doing here is, instead of taking this summation, I'm just taking the I's expected revenue term. So this is, this particular thing here is the expected revenue I will generate. Okay, what is the expected revenue bidder I will generate? Well, if he's of type TI, this is the expected payment he makes, and this is the probability with which he is of type TI. So this is his expected revenue. And so first, I'm going to simplify that term by using the revenue equivalence formula. Okay. So, so I just substitute pi I ti by this. So the first term is a constant. So the, because this is a probability distribution, it just gives you the constant back, pi I 0, right? The second term, I'm going to keep it as it is. So uh, 0 to bi, alpha I ti, ti, gi ti, right? So this is this multiplied by gi ti. So it remains as it is. The third term, again, I'm going to, this has an integral. So it's a double integral here like this. Okay, so this is what you get after substitution of revenue equivalence formula. And then I'm just going to take the third term, which has a double integral, sorry, and change the order of integration in that. Okay, so this is the only trick in this, that because the outer integral, has this gi term. If we integrate that first, we know that we can write it in terms of the CDF. So that's the reason we flip the order of integration here. Okay, so how do we flip the order of integration? Well, you need to think a little bit, because the limits of integration will change. Because if you see, if I take a ti in the outer integral, what are the x's for which this ti will appear? Well, it will appear for all the x's which are above ti, right? So that's why when we change the order of integration, now this integral will run from ti to bi. Okay, of course x's limits are from 0 to bi, because all possible values of x is possible. So this will be from 0 to bi. But for every x, the outer integral ti is valid for ti to bi. So that's why this inner integral limits will change from ti to bi. Okay. So if you're not comfortable with this, try to write it as a discrete type space, and two summations, and you will immediately see when you change the order of summations, the limits of those summations will have to change. Okay, there is also a nice diagrammatic way of seeing it also. Unfortunately, I can't draw it here, but in any case, think about it. If you're not convinced, then we can chat offline also. Okay, so in any case, so this thing comes inside and this goes outside, and this order, once you change the order of integration, then because this is only gi term, so you can now integrate it easily, and this can be written as 1 minus gi ti. Okay. So the advantage of this simplification of this third term is that instead of two integrals, now we have a single integral. Okay, which will be useful in optimizing further. Okay, so any questions here so far? I'm just
How to interpret this last expression?
interpret. So far, I mean, there is no interpretation of this term yet. I mean, I'm going to come to interpretations once I substitute this whole thing and do some further analysis. Anything else?
No, sir.
Okay, great. So essentially, what we can do is, now I can write the expected payment of agent I as pi I 0 plus the first term, the second term here, minus this particular term here. Okay, minus this. Okay, so that allows me some simplification. So which gives you that pi I 0 plus 0 to bi, this particular term. So the way I have done this is, I have taken alpha I gi common here. Okay, so again, this should be gi. Okay, so I've taken alpha I gi common here, and that gives you ti minus 1 minus GITI divided by GITI. So this is like saying that the expected revenue or payment of agent I is this pi I 0 term. So let's forget about this pi I 0 for a moment. But this particular term, okay, here the bracketed term is less than TI. In fact, if so, in fact, what this is suggesting is that the expected revenue collected from agent I is less than basically the expected value he gets. Remember, what is the expected value he gets? Well, it's Ti alpha I Ti Gi Ti, right? And alpha I is the expected probability of winning times Ti. So this is the expected value. But he pays back some of it, right, as revenue. And so the expected revenue, because of uh, 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 individual rationality, it will be something which is lower than the expected value. Okay, so that's what this is kind of reflecting. And so this is the contribution of agent I to the seller if the seller uses this mechanism. Okay. So what we are going to, there's a particular term for this expression, Ti minus this term. It's called the virtual value of agent I. So instead of thinking about the actual value of agent I, which is Ti, the revenue expression is basically a function of this virtual value, which is Ti minus this term, which is a completely a term dependent on the prior GI. Okay, so Ti minus a term which depends on the distribution of values of type of agent I. Okay, so summarizing, expected payment of agent I is pi I 0 plus this the expected virtual value of agent I, right? So that's how we are going to simplify the revenue expression. And of course, because this is the expected payment, what we can do is essentially substitute this here, and we are going to rewrite the objective function. Before I do that, I want to point out some properties of this virtual value function. First, virtual value is Ti minus something, so it's less than Ti. More importantly, it can be negative also. So this term can potentially be less than Ti too. Okay, right? So at this point, I'm not excluding that to happen. So it is possible, depending on how this GI function looks like. It may be negative. So for instance, as an exercise, let's actually take the uniform example. Suppose GI is the uniform distribution and it's distributed between 0 to 1. So BI is 1. So what is this expression WITI then? Any answers? What would be WITI if GI is uniform 0, 1?
1 minus Ti.
0.
1.
So WITI, I'm asking for WITI. What will be WITI?
So 0.
How can it be 0? So
2 Ti minus 1.
So it's going to be 2 Ti minus 1, right? Because so small gi Ti is equal to 1, right? Because it's uniform. And if this is Ti, so it's Ti minus 1 minus Ti, which is 2 Ti minus 1. So you see that below 0.5, it is actually negative. Okay, the virtual value is negative. Okay, so
can we say WITI is the value which seller assumes from agent I? Like it is the value which seller gets from agent I.
yeah, so that's what we are getting. So this is the expected. So the expected virtual value is the expected revenue of the seller. So instead of thinking about the seller's true value, you should the seller should be worried about the buyer's virtual value. That's what the this simplification is saying. Okay. So
How do we interpret the virtual value being negative?
interpret meaning that what do you mean that so I think it will become clearer as we do the optimization, but all I'm saying is like uh, if the seller's virtual value is negative and if we are allocating the object, that will essentially entail that the seller is uh, paying the agent, okay, which he should not be doing if she wants to maximize revenue. And you will see these things happening as a consequence of optimization. Okay, right? So all this is saying is that you need to be careful in awarding the object to agents whose virtual value is negative, right? Because even though the value can be, is always positive, the virtual values can be negative. So you need to be careful because the expected revenue depends on the value, not on the value, but on the virtual value. That's all it is saying at this point.
So you said that the virtual value can be negative, but value will be positive.
Value is always between 0 and BI. Yeah, that's what.
Okay, TI is the value. Okay.
Right? So TI is the value and it's always between 0 and BI. Okay, so another important point, two agents having identical values may have different virtual values. Okay, so TI may be equal to TJ, but because GI and GJ are different, this term may be very different. So if I just looked at values, these two agents would look identical to me. But if I think about their virtual values, these two agents are very different to me. Okay, so that's another important point. Third point is, virtual value map need not be monotone. So basically, as TI increases, it's not clear that this thing WITI will also increase. It will depend on how this term is behaving. So in particular, if small gi by 1 minus capital GI is monotone, then this map will be monotone. Okay. So those of you who know a little, remember a little probability in statistics, this is called the hazard rate of the distribution. Okay. So if the hazard rate of the distribution is monotone, then the virtual value function will be monotone. Okay. But in general, this virtual value function need not be monotone. So as the value increases, virtual value may actually decrease. Okay. So let's keep these three things in mind. Virtual value may be negative. Two agents having same value may have different virtual values. And virtual value map need not be monotone unless the hazard rate, a sufficient condition is that the hazard rate is monotone. Okay, so let's now simplify the revenue expression using this manipulation that we have done. So now the revenue expression simplifies. So this pi I ti, I'm going to replace this whole integral by using this simplification. Pi I 0 plus 0 to bi WITI alpha ITI GITI. Right, so this again, these will be GI. So this is the expected revenue expression of the seller. Okay, so what I have done in the next slide is simplified this further. So this particular expression, what I have done is I have expanded this alpha ITI term, right? So this alpha ITI, we know what it is. Alpha ITI is this particular term T minus I, Fi, Ti, T minus I, G minus I, T minus I, T minus I. Okay, and I've kept the remaining Wi, Ti, Gi, Ti outside. And then I have basically merged these two integrals to write it in a compact way like this. So Wi, Ti, Gi, Ti merges with G minus I, T minus I to get Gt, and this is Fit anyway. So this is like saying that this is the um, basically taking this summation sign inside and expanding this alpha ITI, we get this expression by pure, shifting these integrals and the summations here and there. That's all. Okay. But the nice thing about this expression vis-a-vis this expression is that here we had this alpha I, but now we will have Fi directly because I've just expanded and we can work with Fi directly. Okay. It also has an interpretation. So note here what the interpretation is. So at a type profile T, Witi is the virtual value of agent I. Fit is the probability with which agent I wins the object. So this is the expected virtual value that agent I gets at this type profile. And the summation gives you the expected virtual value of all the agents. So collective expected virtual value of all the agents at type profile T. And this is an expectation over all type profiles. So this basically gives you the expected virtual value from this mechanism. Okay, so that's the interpretation of this. And the revenue expression is basically sum of this pi I zeros plus the expected virtual value from this mechanism. Right? We will do one more simplification here. So far, I haven't used IIR constraint. So remember, the IIR constraint is pi I zero has to be less than equal to 0. Remember, we are interested in maximizing this term, and we have full flexibility of choosing our own pi I zero. There are no constraints on pi I zero. The only constraint is pi I zero has to be less than equal to 0. So in that case, if you want to maximize this expression, then set pi I zero to the maximum possible value, which is 0. Okay. So without loss of generality, we can set all these terms to be equal to 0. So this term basically disappears. So what we are left with is this simple optimization exercise where we have got rid of every possible P term from the revenue expression. It's just an F. The objective function is now completely in terms of F. So the objective function maximizes expected virtual value from a mechanism. But in fact, the virtual value only depends on F. So we are maximizing over all allocation rules the expected virtual value subject to F being non-decreasing in expectation, right? Because now we just have to put constraints on F. We don't, because we know how to compute P's, P's are just such that pi I zero is equal to 0. And pi I would be determined by, once we fix the F, pi i's will have to satisfy this constraint. So we don't need to worry about P's anymore. All we need to ensure is that F is not decreasing in expectation. And we maximize this revenue expression. Okay, so summarizing, we started from this expression, which is maximize the expected revenue like that. It had the P term in the objective function, and subject to FP being BIC and IIR. We changed it or simplified it using our characterization to just an optimization problem in F space. Okay, so our optimization is over all F such that the expected virtual value is maximized. subject to F being non-decreasing in expectation. Okay. Any questions so far? It's very important to realize till this point that all we are doing is using the earlier lectures characterization to simplify the revenue expression. And I have just used simple algebraic manipulations to, and of course the last lecture's characterization to simplify the objective function as well as the constraint set. That's all I have done. Any questions?
No, sir.
Okay, great. So one way to summarize all this discussion is that the allocation rule in an optimal mechanism maximizes the total expected virtual value among all non-decreasing in expectation allocation codes. That's what this is saying. So I choose an F which maximizes the expected virtual value valuation subject to F being non-decreasing in expectation. Okay. Okay, so so far I have just reduced the optimization problem to an optimization problem over F. From here on, the approach will be this is a very simple trick in optimization. If you have an unconstrained, if you have a constrained optimization problem like this, then you first try to solve the unconstrained optimization problem. So basically, maximize this objective function without the constraint that f is non-decreasing in expectation. If it so happens that the optimal solution to that satisfies automatically the constraint, then you're done, right? Because if the unconstrained optimal satisfies all the feasibility constraints, then it's also a constrained optimal. Okay. So that's the approach that we are going to follow. Solve the unconstrained problem first. Okay. So we are just going to maximize this without imposing the constraint that f has to be non-decreasing in expectation. Right? Any questions? So how do we solve this? Okay. So one simple idea here is that let's forget about this integral. Okay, let's forget about this gt dt term. Look at a type profile T, and suppose you were to maximize WIT, FIT. Okay, so here variables, what you have to choose is F, remember? So if you're given a type profile T, how would you choose F's such that this summation is maximized? Remember, F satisfies the following constraint that the sum of FIT has to be less than equal to 1 and each Fi is greater than equal to 0. Right? So
we can say that if WITI is less than 0, then FIT is 0. Or
that is clearly true, right? Because if WITIs are all negative, then there is no point of assigning FIT equal to anything but 0, because that will just decrease the objective function value. So at every t, we should set FIT equal to 1 if I has highest non-negative virtual value. Okay, but if every agent has negative virtual value, then every FIT is equal to 0. If some FITs are non-negative, then basically we should just assign FIT equal to 1 for the agent who has the highest WITI. Then this sum will be maximized. Okay, so this is the solution at every t. At any point t, this is how you should maximize. Is this clear?
Yes, sir.
suppose there are two agents who
Yeah.
has WITI strictly positive.
Yeah.
So we will see which of the agents has highest WITI and we will set FIT is equal to 1 for that agent.
1. Maximum possible FIT value to that agent and 0 to the other.
Okay.
Anything else will be suboptimal, right? So the main point here is that we can do this point-wise maximization here because there are no constraints linking, two type profiles. We have just ignored all constraints. The F non-decreasing in expectation constraints are totally ignored. Now, so to maximize this, we can just point-wise maximize, and that will generate the maximum possible value for this overall expression. Remember, G is always positive. Okay. So then basically this maximizing this point-wise maximizes this overall expression. Then the question is the unconstrained optimal also optimal of the original problem? Well, for that, we need to ensure that this unconstrained optimal rule is non-decreasing in expectation, right? Right. So what we are going to argue now is that that is true if the hazard rate is non-decreasing, that is the virtual value function is non-decreasing. And you can verify that the virtual value function is non-decreasing, if the distribution is uniform and other kinds of distributions. So this hazard rate monotonicity is satisfied by a broad class of distributions, and under that we are going to argue that the optimal of this will automatically satisfy F to be non-decreasing. Okay. And so here is the lemma. I mean, let's first go through this definition carefully. So we'll say that a distribution GI is regular if the virtual valuation function WI is strictly increasing. Okay. That is for all SI TI. If SI is strictly greater than TI, then WI SI is strictly greater than WI TI. Okay.
Regular.
So that would be called a regular distribution. Okay, so as we know that WITI is this, so you see that if this term is non-increasing, then WITI is strictly increasing because TI is strictly increasing. Okay, so a way to ensure that is to assume that the hazard rate is monotone. Okay,
Hazard rate is strictly monotone or only monotone?
Non-decreasing, because this part TI is strictly increasing, so you don't need this part to be strictly decreasing. You just need it to be non-increasing. Okay, so that's all we need. And the lemma basically says that if distributions of all agents are regular, then the unconstrained optimal is also constrained optimal. So what it means is basically the proof is as follows. So we need to show that if distributions of all agents are regular, then the optimal solution that we have identified satisfies non-decreasing in expectation. In fact, what we're going to show is basically a stronger property that F will be in fact non-decreasing. That is, for every T minus I, if agent I increases its type, its allocation probability will increase or weakly increase. Okay, that implies non-decreasing in expectation also. So here is the proof. So take agent I and remember the optimal allocation is deterministic, right? So the optimal allocation here, unconstrained optimal allocation is deterministic. So agent I either wins with probability 1 or does not win. And he wins if he is the highest non-negative virtual value, right? So for non-decreasing, what we do is take an agent I who is winning at type profile TI T minus I. So if he is winning at TI T minus I, she must have the highest non-negative virtual value at that type profile. That's why she is winning. Now suppose agent I increases her type to SI. Well, by our regularity assumption, if she increases her type from TI to SI, her virtual value increases. Okay. But if her virtual value increases at the new type profile, she is the unique highest virtual value. Okay, so according to the unconstrained optimal rule, she continues to win the object at SIT minus I. So what we have shown here is that under regularity, the unconstrained optimum is non-decreasing. That is, for every T minus I, the allocation rule is non-decreasing. And hence, it is non-decreasing in expectation also. Is the proof clear? Okay, if it is not, then you can go back and think about it. So what I have shown is that if distributions of all agents are regular, then the unconstrained optimum, which is this particular rule, is also the global optimum. Okay.
Sir, how are we breaking the ties?
That's not going to matter much because remember it's all continuum, this type space. So whichever way you break the ties, it's not going to affect the revenue because all these ties will occur at zero measure type profiles. So in expectation, it won't contribute to the revenue.
Okay,
So if there are ties, if there are multiple agents who has highest non-negative virtual value, you can just give it to any one of the agents. That's okay. Okay. Or you can use a tie breaking. I mean, you can use a lottery in that case also. But just to make the whole thing deterministic, let's use a deterministic tie breaking. Okay. It won't matter. It won't destroy incentive constraints. It won't affect the expected revenue. Okay, so this is the main result of Myerson. So Myerson basically proves that, which we have concluded now, that if the distribution satisfies regularity, then the following is an allocation rule of the optimal mechanism. So the allocation rule does not award the object if all the agents have negative virtual values. It awards the object to the highest non-negative virtual value agent whenever there is a single agent with non-negative virtual value. Okay. So we know that it's enough to specify this. So first thing, as we argued, that this allocation rule is not only non-decreasing in expectation, but also non-decreasing. So in fact, we can construct payments such that, it will be a DSIC mechanism. Okay. And because it's non-decreasing, we can always construct payments so that the F star, so this should be F star. F star P is an optimal mechanism. From last lecture, if you remember how we can construct payment of this, basically the losers pay 0 and the winner pays the cutoff amount, where the cutoff amount is basically the infimum type at which an agent starts winning. Okay. So basically, if I am agent I and I'm winning, I have the highest non-negative virtual value. Fixing T minus I, you keep lowering my type till my virtual value either becomes negative or I become the second highest virtual value. That is the point which determines my payment when I win. Yes, so that we know from our last lecture that any DSIC mechanism must satisfy this property, given that pi I 0 is equal to 0. Okay. So main takeaway is optimal mechanism is deterministic. It's a cutoff allocation rule. Okay. Payment is basically cutoff payment for winner and 0 payment for loser. Okay. So how do we, interpret, another way to interpret this mechanism is through this virtual valuation function. So look at the inverse of this. Remember, we are assuming that under regularity, this virtual valuation function is strictly increasing. So look at the inverse of that. So there is a point at which this virtual valuation becomes 0. So call that value Wi inverse 0. So that's kind of the reserve price for agent I. So every agent has a personalized reserve price, Wi inverse 0. And if the agent's value is below that reserve price of his, then he is not considered in the mechanism, because then its virtual value is 0 and you don't consider. You're only considered if your value exceeds that reserve price Wi inverse 0. And then amongst the agents who are considered, we choose the agent who has the highest virtual value. Okay, so that's another interpretation of this. Optimal mechanism is deterministic. It satisfies DSIC and it satisfies ex post IR. Even though, to start with, remember, we searched over the set of all randomized BIC and IIR mechanisms, but the optimal mechanism is very special. It is deterministic, it is non-decreasing, and it satisfies ex post IR. Okay, so the payments that we constructed satisfies ex post IR. Okay, so any questions?
It satisfies BIC and IIR. So why we are writing DSIC and ex post IR?
Right, because we saw that if we assume regularity, then this particular rule is non-decreasing. Okay, it satisfies the stronger property of non-decreasingness rather than non-decreasingness on expectations, right? We saw that. So the proof of the lemma basically shows that the optimal rule is non-decreasing, satisfies the stronger property. We know that if a particular allocation rule satisfies non-decreasingness, we can always construct payments so that F star and P becomes a DSIC mechanism, right? We know that any non-decreasing allocation rule can be converted to a DSIC mechanism. Okay.
So this result follows from the theorem in the previous slide.
Theorem that
So the BIC can be converted to DSIC.
that's are you talking about the BIC DSIC equivalence result that I stated in the last slide of the last lecture?
Yes, sir.
No. So that is that is a much deeper result. So that says that for every BIC mechanism there is a DSIC mechanism. Here I am stating a very simple fact. Okay, it's just a simple observation. So we started imposing BIC and IIR constraints. When we solved for it, we found that the optimal allocation rule is something which satisfies non-decreasingness condition. Okay, we know from our earlier theorem that any non-decreasing allocation rule can be converted to a DSIC mechanism by appropriately choosing the P's. Remember, this F star is only an allocation rule. I can always choose the P's so that F star P becomes a DSIC mechanism. And how do we choose it? Choose these payments. Well, these are just the cutoff payments, right? So that's what we know, that if you have a deterministic DSIC, I mean non-decreasing allocation rule like this, then if you choose the cutoff points as your payments, then that becomes a DSIC mechanism. Okay. So then the question is, I mean, essentially, the confusion here is that how, we started out with this problem. Here we said that we can forget about p's. Whatever p we choose, it's not going to matter, because the revenue expression only depends on f. Okay, and we know that from our revenue equivalence formula, that if you choose p according to that revenue equivalence formula, it will always satisfy the incentive constraints. Okay, so here what we have done is, basically, once we saw that f satisfy a non-decreasingness condition, we chose p such that it satisfies DSIC constraints. Hence, it will also satisfies BIC constraints. Okay.
So what we're saying is that there may be other payments which only satisfies BIC, but does not.
Exactly. Of course, we can always choose other kinds of payments which will only satisfy BIC constraint. But because f star satisfies non-decreasingness, I can always choose this payment so that it satisfies DSIC constraints.
So, sir, can this now be implemented in BIC? I mean, in first price auctions.
In first price auctions too. So I'm going to come to that. Yeah, I'm going to come to that. It can be implemented both as second price as well as first price auctions, and we'll come to that. Okay, so you can have the same allocation rule being implemented such that basically let me step back a minute. We can have two formulations of the optimal mechanism, both of them having the same interim allocation probability and interim payments, but one of them having DSIC implementation, the other one having BIC implementation. Okay, but what I'm telling you here is the DSIC story, that because F star is one of the optimal solutions, is that F star has this non-decreasing property. I can always choose P such that the incentive constraints are satisfied with DSIC. Okay, so of course there are alternate implementations also. Yeah, so it's important to realize that the result here is telling you one optimal solution. Okay. One implementation of the optimal solution. Okay, so what we have said, what we have concluded so far is that the optimal mechanism is deterministic, because it only awards to the highest non-negative virtual value guy with probability 1 and otherwise 0. The payments can be determined using the DSIC formula. So it's the cutoff payment for winners and 0 payment for losers. And as long as it satisfies DSIC constraints, it will also satisfy BIC constraint. And because of our reformulation of the problem, this has to be an optimal solution. Okay, and yes, so maybe for today it's enough. Let me stop here on I have some examples, or maybe I take another 15 minutes to finish this part also. Yeah, let's finish. So one of the interesting cases, so this formulation of the mechanism is quite complex, because we don't know which WI is winning and so on and so forth. One simple case is when agents are symmetric. So suppose the type spaces of all the agents are the same. So B1 equal to Bn. Okay, so everyone is drawing from the same support and all the GIs are same. So ex ante, all the agents are symmetric. In that case, the virtual valuation function is the same too, because remember what the virtual valuation function is. This is like this. Because the GIs are the same, for every agent, this virtual valuation function will be the same. Of course, at a type profile, different agents will have different virtual values, but the function will be the same. So you can remove this W subscript I from this function. Okay, because the GIs are the same. So the virtual valuation function becomes the same. And so let's denote this function as W. Okay. And so this is the only one, one single virtual valuation function for all the agents. And for remember, one important point in this virtual valuation function is the point where the virtual valuation function crosses the 0 point. And so that's your W inverse 0. So now everybody has the same reserve price W inverse 0. So if all the agents lie below W inverse 0, then the object is not allocated. If a single agent lies above W inverse 0, its value, then whoever has the highest virtual value wins. But remember, everybody has the same virtual value function. So because of regularity, highest value also is the highest virtual value in this case, right? Because if everybody has the same virtual valuation function, whoever has the highest value will also have the highest virtual value because of regularity. Okay. So in this case, at least the auction or the optimal mechanism simplifies. If all the agents have value less than W inverse 0, nobody gets the object. Otherwise, whoever has the highest value, he gets the object. Okay, so that's what I have summarized here. If agents are symmetric and distribution satisfies regularity, the common distribution satisfies regularity, then if everybody's value is less than this W inverse 0, then nobody gets the object. Otherwise, whoever has the highest value, he gets the object. Okay, so of course, we know that the payment formula for that is, winners pay, losers pay 0, but the winners pay the infimum time at which she wins. But what is the infimum time at which she wins? Well, she has to be the highest virtual value, highest value in this case, or she has to beat this W inverse 0. So the infimum will be achieved at max of W inverse 0, max of J not equal to ITJ. So maximum of the second highest value and the reserve price. Okay, so that will be the payment of the winner. But this is exactly a Vickrey auction with the reserve price W inverse 0. Okay, so at least when the agents are symmetric and the distribution satisfies regularity, the optimal mechanism is just a Vickrey auction with a reserve price W inverse 0. That is, if everybody has value below this reserve price, nobody wins. Otherwise, whoever has the highest value wins, but makes a payment equal to the maximum of the second highest value and the reserve price. So this is one key takeaway, the simplest takeaway from Marston's exercise, that the optimal mechanism in the symmetric case is just a Vickrey auction with reserve price. Coming back to the alternate implementation, we can have the same revenue from a first price auction also. If you do a first price auction with a reserve price W inverse 0, that will also generate the same revenue, but it will only satisfy the BIC constraints. Okay, so the idea is you post a reserve price of W inverse 0, ask agents to bid. Whoever has the highest bid which exceeds this reserve price wins the auction and pays an amount maximum of the reserve price and the bid amount. Pays his bid basically, because by definition, if he wins, his bid is greater than the reserve price. So you can show that basically the first price auction with a reserve price like this would also generate the same revenue. Okay, but that will only satisfy the BIC constraint. So here is an example, worked out example. Let's go through this so that we understand some delicacies and intricacies of this. So the example is with two agents. One agent has support 0.12, the other has support 0.18. Both the agents' values are distributed uniformly in this support. So that means that agent 1's virtual valuation, we saw that the virtual valuation is 2T1 minus the upper support of the interval, which is 12. And for the second agent, it's 2T2 minus 80. Okay. So in essence, agent 1 is facing a reserve price of 6, because if he has value less than 6, he will not be considered. His virtual value is negative. Agent 2 faces a reserve price of 9. So let's look at some type profiles and see how the auction will proceed. At least in these type profiles, what will the optimal auction do? Look at the type profile 4-8. Well, at 4-8, both the agents have negative virtual value, right? 8 minus 12 and 16 minus 18. So the object is not sold. Well, if the object is not sold, both the agents pay 0. Losers pay 0 in our auction. If the type profile is 7 and 8, then agent 1 has positive virtual value. Agent 2 still has negative virtual value. Okay. So agent 1 wins the auction, but because he's the only agent who has positive virtual value. What is her payment? Well, we need to look at the infimum type at which she starts winning. What is the infimum type at which she starts winning? Well, she just needs to have positive virtual value. And the first point at which she has non-negative virtual value is 6. So her payment in this case is 6. Okay, and loser doesn't pay anything. Notice here that the auction is inefficient, even though agent 2 has a higher value. Because her virtual value is lower, she is not allocated the object, and agent 1 gets the object. Okay. Here is another point at which both the agents have positive virtual valuation. See, this guy has 10 values, so virtual value is 8. Agent 2 has 12 values, so her virtual value is 6. But virtual value of agent 1 is still higher, so agent 1 wins. But now, what is the infimum type at which she starts winning? Well, she has to beat agent 2 also now. So remember, agent 2's virtual value is 6. So what is the point at which this expression turns 6? Well, exactly at 9. Right? So that's when she starts beating agent 2 now. The non-negative virtual value constraint is not binding, so that is lower. So what agent 1 pays is 9 in this case. Okay.
Can you explain this again?
The third one.
Yeah.
So
Yeah.
why agent 1 pays 9?
Yes, sir.
So we know that what is the payment of an agent? It is the least type at which she starts winning. Okay. So what is the least type of agent 1 at which she starts winning? Agent 2's type is fixed. So her virtual value is 9. Right. So 2 times 12 minus, her virtual value is 6. Sorry. 2 times 12 minus 18, which is 6. Okay, so her virtual value is 6. And so basically, what is the least type at which the virtual value of agent 1 is non-negative and exceeds 6? Well, the agent 1 virtual value becomes non-negative at 6. But to beat the virtual value of agent 2, she has to have a virtual value of 6. And at type T1 equal to 9, she has a virtual value of 6. So the least type at which agent 1 starts beating agent 2 is 9. Okay, so that's the cutoff payment. Is that clear?
Yes, sir.
Okay, so the DSI, once you fix an allocation rule, non-decreasing allocation rule, because the payment at the lowest type is set equal to 0, there is a unique way you can determine these payments, and that's what I'm using here, the cutoff payment. Okay, That's what we have been told by the revenue equivalence formula. So we just use that and compute these payments. Okay. So the whole deal is to figure out what the allocation is. Once you figure out the allocation, we know how to compute the payment. Okay. The last one is T1 equal to 8 and T2 equal to 15. In this case, 8 is this virtual value is 4 and this is 12. So agent 2 wins in this case. Agent 1 pays 0. What is the least type at which agent 2 wins? Because agent 1's virtual value is 4. So what is the least type at which agent 2 has a virtual value of 4? Well, that's 11, right? Because 2 into 11, 22 minus 18, 4. So that's why agent 2 pays 4. Okay, sorry, pays 11. Okay, so because that's the point at which she has virtual value 4. Okay, so what we saw from this example is that the optimal auction in the asymmetric case where bidders have different supports need not be efficient, and this inefficiency is because of two reasons. Sometimes the objects are not sold, the object is not sold even though both the agents have positive value. Sometimes it is sold, but it's sold to the lower valued agent, like here and here. Okay, so it's sold to the lower valued agent. So optimal auction need not be efficient. Okay, in the case where the agents are symmetric, it is efficient whenever it is sold, right? Because you always award the object to the highest valued agent whenever you award the object. But still, another source of inefficiency, which is that sometimes you don't sell the object, remains even if the agents are symmetric. Okay, so that's a key thing to remember from this exercise. So just to conclude, this Meyerson's approach of solving this revenue maximization problem is basically, you should look at it as a toolkit. Okay, why is it a toolkit? We have this characterization of DSIC, BIC mechanisms. So many one-dimensional mechanism, those characterizations go through in many other one-dimensional mechanism design problems. As long as your type is just one number, which is the case here, which is the value of the agent, many of these problems can be characterized by similar kind of non-decreasingness and revenue equivalence formula. And then basically what Meyerson suggests is basically a four-step approach. First, use IC and IR characterization to simplify the revenue expression. Reduce the optimization space to allocation rules using those simplifications. Solve the unconstrained problem. Verify that the unconstrained optimal is constrained optimal. It's kind of a step-by-step procedure on how to solve this optimization problem.
Sir, what if the unconstrained optimal is not constrained optimal?
Yes, I'm coming to that. Extensions. So what happens if the regularity is not satisfied? Okay, so if the regularity is not satisfied, the problem is that the virtual value is no longer monotone. So what can happen is like you allocated a type to the agent with the highest virtual value. Then this agent basically increases its type, but its virtual value decreases. So as a result, in the new type profile, he's no longer allocated. So that's basically, violating the non-decreasingness property. So the actual rule will not be, need not be non-decreasing in expectation anymore. So that case is more difficult to solve. Meyerson in his paper has solved that case also. That optimal auction or mechanism is quite complicated. It involves a technique called ironing. So you should remember this term, ironing. What exactly is ironing is, you should read the paper. it's very difficult to convey it in one single lecture or anything. It will take more time. Okay, so I'm leaving that for you. If you're interested, you can read it, because regularity is usually a very common condition. Most distributions satisfy it. People only specify results under regularity. Okay, but it is possible to solve, and it will have all these properties. It's a deterministic mechanism, it's DSIC and so on. Just that it's difficult to express how you should allocate it. Okay, so the iron virtual value is a complicated term. The other extension is, what if there is a cost for the seller? So basically, the seller is only willing to sell the object if he gets a particular, revenue from the mechanism, right? So he wants to keep the object if the payments are low. Okay. So results go through with some modifications to the virtual value. So you put in the cost thing in that and rewrite whole thing. Only change is that the cost function becomes a little different. The virtual value function becomes a little different. Okay.
Isn't it just a shifting of the entire
It's
problem?
a shifting of the origin essentially. Okay. There is a separate problem which is called the monopoly pricing problem. It was solved earlier than Marson by Musa and Rosen. In my notes, there is a section called the one agent problem. In that section, basically, I have completely written down how you can solve this problem using the techniques that I have described now. You should read it. I'm not going to have a separate class for that. So in that problem, the problem is slightly different but very related. So there is a seller which can produce a good at different quality levels. So this instead of allocation probability, there is a quality level between 0 and 1. So the Fi basically indicates the quality level of the product. Okay. There is a single agent. Okay, so this is not a problem with multiple agents. You can also do a multi-agent version of it, but at least the one agent problem is interesting enough, so you should look at it. They also solve the one agent problem. So the agent has a per unit value for quality. So if you get a quality Q, your value will be V times Q. Okay, so there's a per unit value for quality. Seller has a convex cost for quality. Okay, so basically there is a cost function C. So to produce a quality level Q, there's a cost C of Q, and this cost function is convex. Whole thing that I did in the Myerson framework, in the single object allocation framework, very similar approach. You can solve this problem also. And in the notes, I have exactly solved this, and you should take a look. Okay, so I conclude by saying that the Myerson technique is quite general, and it can be applied to a variety of problems. By tonight, I'm going to send you an assignment which has a variety of problems, all where the type of the agent is one dimensional, that is only one number. And you can use Myerson techniques to solve those problems. And you should try how those things work out. Okay. Any questions?
Yes. So just I want to know the interpretation of the reserve price.
Interpretation of the reserve price in this world, in this sense. What is the interpretation of W inverse 0?
Yeah.
So essentially, the reserve price is basically the seller is saying that I will only sell if the buyers have high enough value. Okay, and the reserve price basically also comes in the payment. So basically, the advantage of the reserve price is that you collect more revenue, right? So, for instance, if only one agent has value greater than W inverse 0, Then if you didn't have the reserve price, then this guy will pay an amount equal to the second highest value, which may be lower than the reserve price. But if you put a reserve price, then the revenue at those profiles will increase. Okay, so that's basically the intuitive idea why a reserve price comes out naturally, endogenously in this optimal mechanism. Okay, so it boosts up the revenue, just like in the one agent case. If we didn't have a reserve price, then we'll sell the object all the time and collect zero revenue, right? And so the choice of this W inverse 0 is basically chooses this reserve price optimally. One criticism of the Meyerson type of work is that these things depend heavily on priors. So the W inverse 0 is computed from the distribution. Remember, W is a very distribution heavy function, right? So it depends on the distribution. So if as a seller you are not sure about the distributions from which the types are drawing their values, then Meyerson's work is less useful, because we don't know how to how to set the reserve prices. So the optimal mechanism clearly depends on the details of these distributions.
We
But
generalize it in that case by saying we can calculate expected virtual value by further taking some distribution over GI.
wow, distribution over the distributions. That okay. Yeah, I'm not sure if that would work, but yeah. So there is a lot of work about formalizing exactly how you would go about doing if you don't know any priors. So in a prior free world, how would you do revenue maximization? So the basic problem is that if the seller doesn't know any priors, then how does he formulate revenue maximization? Right? Because he has to choose a mechanism based on what he expects will happen in the mechanism. If he doesn't have any priors, then how does he compute an expectation? So that's the problem. So Meyerson's solution is only possible if as a seller you have some idea about the distribution of values. Okay, let me stop here. So I noticed that I have been going like above 10-15 minutes every class. Maybe next class will be a smaller class, about 45 or 1 hour or something like that. And
Can we also do it like if we can run some other mechanism to extract out the exact priors of the agents? So from that mechanism, whatever priors we get, we can use those priors in this setting.
yeah, so that's possible. So you ask agents to report the distributions. So remember, now this mega mechanism has to be incentive compatible.
Or we can treat that mechanism as a separate mechanism, and
How can it be separate? Because the outcome of that mechanism will influence the outcome of the second mechanism, right? So it has to be treated as a mega game.
Okay, sir.
Yeah. Okay, so see you again next Monday. And I'll send you the assignment by tonight. Okay?
Okay, sir.
Okay, sir.
Bye.